Good morning, all of you. I'm Shivansh. I'll be presenting in a course in the form of an overview. Name of the course is Introduction to Aerospace Engineering, Astronautics and Human Spaceflight. This course is offered by MIT, Massachusetts, via platform named edX under the mentorship of Professor Jeff Hoffman, who himself was an astronaut. Now jumping right to the main material, I have divided the course content into three modules just so as to make it easy for me to explain. The first module is Introduction to Engineering and Aerospace Engineering. The second module gives a brief account of rocket propulsion systems. And the third module includes the world of microgravity. So let's get started. What is engineering and aerospace engineering? I want to start by taking a look at engineering in general. Human beings have actually been doing engineering ever since they came and first learned how to make tools out of stone. And there have been some incredible engineering accomplishments throughout the course of human history. There are some basic principles which apply to all types of engineering. Let's take a quick look at some of the things that engineers have to be conscious of when they are doing their work. First of all, engineers rely on what they understand about the natural world around them, and they use scientific discoveries as the basis for the constructions, the designs, the things that they're actually going to make, so that we can actually harness the aspects of the physical world around us to make useful objects. And usefulness is another critical aspect of engineering because we don't do engineering in a vacuum, right? And here I'm not talking about aerospace engineering, I'm talking about engineering in general. Engineers are a part of society. One of the first things that you have to do is to identify a need for something that doesn't exist or something that is already in existence but has some problems which you can maybe improve. So we have to be conscious as engineers of our role in society and look at societal needs as a driving force for what we do in engineering. And once we identify a need, then we have to devise the processes, the equipment, basically the systems that we use to solve those problems. And I want to concentrate on communication as a part of engineering. Being able to communicate is critically important. You can have great ideas, great designs, but if you can't communicate those ideas to other people, then you are really not going to have success in being able to realizing your concepts. Communicating ideas thus is absolutely critical for success of an engineer. Let's move from engineering in general to take a closer look at what's involved in aerospace engineering. It would be nice to think of aerospace engineering as learning to fly in three dimensions. Leaving the surface of the earth, flying through our atmosphere out into space. One of the things that is fascinating about aerospace engineering is that it involves a tremendous number of subdisciplines. Let's take a brief look at what the qualities are that someone needs to be an aerospace engineer. And to do this, let's have a look at a document made by the Boeing company on the basis of many, many years of experience in large engineering projects. First of all, to be a successful engineer, you have to be good at basic science and math that you are going to be using throughout your career. And of course, nowadays that includes competency with information technology as well. We build things as engineers, and when you're working for a company which is going to build large numbers of aerospace systems, then it's very important that when you are designing something that you understand how that object is actually going to be manufactured and used. Even if you are only at the beginning of it in designing, you have to be able to imagine how your system is going to operate right throughout the end of its life. and and engineering is multidisciplinary. To be successful, even if you are working on the structures and materials part of an aerospace system, you better understand how that relates to the propulsion and the control systems. And basically, a systems perspective is a critical part of aerospace engineering. Now, let's look into how we propel rocket structures. We are available with several rocket propulsion systems like chemical rocket propulsion, electric rocket propulsion, etc. Here we have a solid rocket motor or booster, which is a type of chemical rocket propulsion system that uses solid fuel. Right. Here, just I want I want you to just look at this size of this section of the inside of the solid booster compared to the people around it. This is huge, isn't it? The gases or fluid flow out of this section in the booster and go out right to the end of the booster, giving an immense thrust to the rocket structure. Chemical propulsion also includes liquid rocket motor or liquid rocket propulsion, but that's a bit complex. This one right here is a bit easy. The disadvantage with it, though, is that it's hard to control. Once it's lit, it's just gonna go. It cannot be controlled in its way. A simple example of a solid fuel powered rocket is a firecracker rocket that we use in celebrations. The use of solid rockets dates back many centuries to the introduction of fireworks by the Chinese. In modern day aerospace engineering, however, solid rockets are still used in a number of applications, from sounding rockets that carry scientific experiments into suborbital flight to the enormous solid rocket boosters that helped propel the space shuttle out of the Earth's atmosphere. This one right here is an electric propulsion motor. It's kind of small, but it only works in vacuum. It can be taken as its drawback or disadvantage. Now we delve into the world of microgravity. Let's start off with a simple question. What causes weight? You may be tempted to answer that it's gravity. Well, that's actually not the whole story. Weight is actually caused by the earth pushing back up against you with a force equal and opposite to gravity, as dictated by Newton's third law. In fact, if gravity is the only force acting on an object, then that object is in free fall and has no weight. Spacecrafts are also in free fall because gravity is the only force acting on them, which induces centripetal acceleration and keeps them in orbit around a celestial body. Among the many differences between life on Earth and in orbit, perhaps the most prominent is the sensation of weightlessness in space. Often we hear the term zero gravity that's used to describe this phenomenon. However, this is a misnomer. Although the force of gravity is reduced, it is never actually zero, even in deep space. In fact, without gravity, it would not be possible to keep spacecraft and satellites in orbit. Instead, a more accurate term would be microgravity, which is equal to 10 to the power minus 6g, and g here refers to the gravitational acceleration that we experience here on Earth. A lot of effects of space on the human body have to do with the lack of normal effects of gravity. There are a lot of different words which get used for the gravitational condition in orbit. Technically, we talk about microgravity. Actually, it's very important to realize that when you are in space, we don't really have zero gravity. You can see here the expression that Isaac Newton developed for gravitational force inversely proportional to the radius, right? Here, to really be in a situation where you had zero gravity, you'd have to be an infinite distance away from any objects which have gravitational pulls. And of course, that's not true. There is gravity in Earth's orbit. If there wasn't, we wouldn't be going around the Earth. We'd simply go shooting off in a straight line. In the end, I thank you all for joining in this short lecture. And now, if you have any questions, you may ask.
So do we have any questions from the student side? I hope the slides were very nicely prepared, uh, Shivansh, first thing, and
Thank
it was very nicely presented as well. So everybody have understood the three modules which Shashank had discussed. So if anybody has any questions in their mind regarding this particular thing, so he can ask, or what he understood from this course or anything else he want to know about. Meanwhile, Shivans, what is the duration of this particular course?
Sir, it was 2 months.
Okay, so in 2 months, what you have covered, just a brief about,
Yes,
all
yes.
these theoretical part, or is there any practical implication is also there?
So there were numericals as well, a lot of numericals, but I thought let's do the things from which uh, the students can learn something. Because numericals in 8 to 10 minutes were difficult to explain.
Hmm. So what exactly at the end, what exactly you learned from this particular course? What do you feel?
So the assumptions that I had about how astronauts live in space on the International Space Station and how we propel rocket structures. Uh, there were, I mean, I thought, how would the astronauts live in ISS?
Hmm.
There, they taught how they breathe air into ISS and how they keep themselves healthy. The longest duration that an astronaut have had on ISS was 1 year. It was back in about 1970, and
Hmm.
they talked about how what health effects do astronauts have when they come back to Earth, and several such things.
But recently, I hope you know that the first lady for the longest time she stayed. I think I'm not remembering her name.
Sunita
And
Williams.
no, not Sunita William. This is
Yes.
the latest news. I don't know, Lady Gargin or something. She also led the first crew, first for all women crew. She walked into the space, and chalo, that's a part question. You talked about ISS. Which orbit is in ISS's? Do you know orbits of Earth?
Yes, sir. It was low Earth orbit, but ISS foreign. Yeah, it's in low Earth orbit.
Okay, okay. And you talked about rocket propulsion system
Yes, sir.
a little bit. So, what is the stage of rocket propulsion system in India? At what stage we are? You do you know about that also?
Rocket propulsion. Yes, sir.
Yes.
I've heard, watched videos on YouTube that we
Mhm.
use at this time cryogenic fuel engine. It
Hmm.
has a kind of it's hybrid. It's not completely chemical rocket propulsion. It's a hybrid kind of stuff.
It is indigenous.
Mm, yes, it's indigenous. A scientist, by the way, went through all that process of cases. Name was, I guess, Narayan Prasad. Yeah, he had a lot of problems. He was developing the cryogenic fuel engine before even NASA. But the CIA that had some, I mean, they sent him into jail and he had a lot of problems.
All right.